Hello, Assalamualaikum. My name is HAZIQ SYAUQII by HELMI. My metric number is B0821101178. And my group member is Muhammad FAIZ bin SHALIHIM B0821101166. Today I will present the conduction graphical analysis on heat transfer. For this presentation has 5 content. First, introduction. Second, design. Third, analysis. Fourth, discussion. And fifth, conclusion. Introduction. What is a heat sink? A heat sink is a passive heat exchanger that dissipates heat produced by an electrical or mechanical device away from the device and into a fluid medium, either air or a liquid coolant. This allows the temperature of the device to be controlled. A material with a high thermal conductivity like copper or aluminium is frequently used to create heat sink. They have a lot of surface area which help disperse heat, and they frequently feature fins which add to the surface area. A fin surface is a heat sink that has been extended with fins to increase its surface area. The fins help to increase the rate of heat transfer by providing more surface area for the heat to be transferred to fin surface. Are often used in application where a large amount of heat needs to be dissipated, such as in computer and power supply. The fin help to keep the device cool by transferring the heat away from the heat source and into the surrounding air. Objective: learn how to sketch using SolidWorks software, manage to run the heat transfer simulate to show the temperature distribution along the heat transfer surface fin in the free and forced convection, and to create two different fin surface according to our creativity using SolidWorks software. This is our first design. The ambient temperature is 28 to 34 degrees Celsius. Fin base size is 40mm times 40mm. Convection coefficient is 5.03 watt over meter square. Average heat flux on cold sides is 1.5 kilowatt over meter square. Average temperature on cold side is 76.6 degrees Celsius, and average temperature on hot side is 97.3 degrees Celsius.
So next is the design 2. The design 2 ambient temperature is 28 degrees Celsius until 34 degrees Celsius. Fins base size is 40 mm times 40 mm. The coefficient is 5.03 watt over m square times Kelvin. Average of the heat flux on cold side is 1500 watt over m square. The average of temperature on the cold side is 76.6 degrees Celsius. Average temperature on the hot side is 97.3 degrees Celsius. So this is our analysis from both our design. So basically we have two design here. As you can see, this design design 1 have more fins than the design 2, and the design 1 dissipate heat is uniformly from red to the blue. The blue is the coldest point of temperature, and the red one is the hottest temperature. So the coldest temperature is 3.2 exponent power of 2, and the hottest point of temperature is 0.2 exponent power of 2. For the design 2 is not so good. As you guys can see, there is only two fins that are blue, which is the coldest point. So the blue is 3.04 exponent power of 2, and the hottest one is 3.714 exponential power of 2.
This is the analysis for our first design. The graph is shown the thermal result for the fin surface at the first design, and then this is our second design thermal result. The temperature, the maximum temperature for design 2 is 3.714 Kelvin.
The discussion for this assignment is fin efficiency is a measure of how effective a fin surface is at transferring heat. It is defined as the ratio of the actual heat transfer rate to the theoretical heat transfer rate. The theoretical heat transfer rate is the heat transfer rate that would occur if the fins were infinitely long and there was no airflow. The actual heat transfer rate is the heat transfer rate that occurs in a real world situation. Fin efficiency can be increased by increasing the length of the fins, increasing the number of the fins, increasing the airflow, or increasing the airflow. The optimum fin efficiency will depend on the specific application. So from this assignment, we can conclude that design 1 is the conduction heat transfer scheme that works the best. This is because the design structure has more fins than the design 2, which can increase the efficiency of conduction heat transfer since heat can move more quickly between each fin. This design is appropriate for the product because it has more fins on the surface that protrude from the object, which increases convection and speeds up the rate of heat transfer to the environment. So that's all for our presentation today. So thank you. Assalamualaikum.